Hi, we're Team TCH, and we are leveraging advanced natural language processing methods to help Texas Children's Hospital manage their large quantities of patient data. At Texas Children's Hospital, nurses have to manually parse clinical notes to extract specific patient features that can be input to a clinical database. This process can take upwards of 10 minutes per clinical note. With thousands of patients per year and multiple notes per patient, there are tens of thousands of clinical notes. This quickly adds up to thousands of hours of work. Our job is to help automate the process of extracting information from clinical notes that can be input to the PC4 research database.
There's a total of 9 fields that we need to extract from the clinical notes, divided into 3 categories: numericals, booleans, and definitions. We have a total of 2,500 clinical notes in the dataset with the average size of 40,000 words per patient. As you can see from the plot on the right, that most documents don't miss any fields or miss just a few of them. For the data exploration, it was very helpful to manually go through the notes and discover the average length of the label, number of occurrences of each field per document, and also the format in which fields are entered in the clinical notes. For the data wrangling, we combined all the documents in one place, organized them by patient, and dropped clinical notes that have no entities in them and are not represented for training. We later confirmed the accuracy of all labels and made an easily accessible document. The first part of data pipeline is label mapping, and we need to represent all the documents in the training dataset in the following format, listing all the indices at which the fields occur in the clinical notes. For feature mapping, actually finding the occurrences of the labels in the clinical notes. For numericals, we just looked for the exact value of the integer of the float. For syndromes, we looked at the most unique word in the descriptions, and for booleans, we looked for the words antenatal and premature. And here are the results of our feature mapping. As you can see, we perform very well in the syndrome description.
We found a lot of the simpler fields using a sort of rule-based NER, where what we did is we looked for the keywords such as birth weight, and then we looked for the respective value type next to that field. So for example, birth weight and a numerical value. For numerical values, we were actually able to get a recall of about 75%, giving us 18,000 correct entries. And with the Booleans, things weren't as great, only getting about 19% with antenatal and 45% with premature. But this also does not include mislabelings of the data, so if the nurses transcribed it wrong, or if the entities were never recorded in the first place. And there are, of course, different abbreviations and typos and things like that that make this scheme a little bit more complex.
One technique we used for the modeling and extraction step of our data pipeline was SPACY. SPACY is an industry-standard natural language processing framework. Let's take a look at the SPACY model we trained. The SPACY model we trained has 2 components, shown in red here on the screen. The first is the transformer. It takes the labeled training data as input, and it breaks it into chunks called tokens and turns those chunks into vectors, as shown on the screen. And it preserves the labels such as date, birth weight, and chromosomal abnormality during this step. During the second step, which is the NER step, it learns to recognize these named entities from new unseen text. When it's finished, it saves the parameters, the weights and biases of this trained model so that it can be used later for evaluation.
The next step was to evaluate model performance. We used precision, recall, and F1 score to measure accuracy on individual PC4 fields. Overall, precision emphasizes accuracy relative to the number of false positives, recall relative to false negatives, and F1 score balances the two. Displayed here are the metrics on the PC4 fields. We can see the model does quite well on detecting chromosomal abnormalities. Furthermore, precision on syndromes is also quite high. However, the rest of the scores are quite mediocre and either have about 8 to 9% accuracy or were never tagged at all. We also create an aggregate metric, the per patient detection accuracy or PPDA. The PPDA is the average percentage of a patient's PC4 database entries that our model extracts. The PPDA is quite low at 1%. Upon investigation, we found that this is because a large portion of PC4 entries solely contain numerical fields, whereas the current model only performs well on string-based fields.
To achieve the best results, we combine the entities extracted by SPACY with the entities extracted by the rule-based NER. And then we compute the recall for each entity by dividing the total number of detected ground truth labels by the total number of ground truth labels for that entity in the test set. And then we look at our results and we see that 3 of our numericals perform really well overall, and our 2 Booleans perform really well as well. But our last 2 numericals don't perform that well, and syndrome and non-cardiac abnormalities don't perform very well either. So moving forward, we want to look more closely at the parts that the model didn't perform that well in and see what we can improve in terms of the rule-based NER and label mapping. And we're also thinking of taking a semi-supervised learning approach as well to see how that would perform for our problem.